Okay, we are on exit ticket 17.4, LeChatlier's principle. It's on the back of your 17.3 equilibrium exit ticket. So you need to kind of review the front of this, the rules for equilibrium, what an equilibrium is, before LeChatlier's principle will make sense to you. When a system is at equilibrium, it's balanced like a seesaw, and the rate of the forward reaction equals the rate of the reverse reaction. So you start off with a system with 0 products, 100% reactants, and after a certain amount of time, they even out. The rate of forward and the rate of back even out, so the concentrations have stabilized. The molecules are constantly in motion, trading between reactants and products, but it's happening at the same rate. Equilibrium systems, just like all systems, respond to changes in their environment or stresses. In a chemical system, they do this by shifting the direction of the reaction to accommodate the stress. So we're going to break that down and talk more specifically about what that means. First, I want you to look at this reaction. We've got N2, 3H2 making 2NH3. On this side, we have 4 moles of gas. On this side, we've got 2 moles of gas. And it's exothermic, it's giving off heat. So we're thinking that of heat as a product, and it's really important for these thinking and exercises that we're going to be doing that you think of heat as either a reactant if it's endothermic or as a product if it's exothermic. There are 4 moles of gas on the left, 2 moles of gas on the right. So here's a couple questions. If you were to add heat to this reaction, you're adding heat and it's trying to give away heat. You're actually stressing the reaction by adding more heat. If you add more heat to this reaction, it's going to make the reaction go backwards. You're adding more of this, let's think of it as a product, it reverses the reaction. So it would slow down the production of ammonia and increase the decomposition of ammonia into nitrogen gas and hydrogen gas. If you're to add more N2, that's adding more reactant, it's adding more ingredients, you're more likely to make the reaction go to the right and make more NH3. So these are the kinds of questions that we're going to be asking and looking at and investigating. So LeChatlier's principle says, French chemist LeChatlier said, if a change in conditions, stress, is put on a system which is at equilibrium, the equilibrium position will shift to reduce the stress and reach equilibrium again. Remember, we have equilibrium constants, and they're equal to our concentration of our products over the concentration of our reactants. The ratio is going to stay the same. So if you change the products, the reactants have to change correspondingly for the equilibrium constant to be a constant. So when we say the position is going to change, we're going to say, are we going to favor the right side or favor the left side of this reaction? We stress equilibrium by doing one of the following things. If you change the concentration of reactants or products, if you change the pressure, if it's a gas system, and if you change the temperature, exothermic versus endothermic, those changes will be opposite of each other in the way that the system responds. But all stress factors shift the reaction in order to reestablish the balance so that KEQ is still true. A shift means the reaction reacts predominantly to the left or to the right to reestablish the balance. It's either going to favor the products or the reactants. So if you change the concentration, if you add a reactant, if you add something on this side, it pushes the reaction to the right. If you add product, if you add something over here, it shifts the reaction the other way, shifts it toward reactants. So adding things, adding acts like a push. If you add something on this side, it pushes it the other way. If you add something on this way, it pushes it to the right. But removing things acts like a pull. So if you remove a reactant, one of these guys, pull it out, it pulls the reaction toward the left. If you remove a product, something on this side, it pulls. Pulling, removing stuff pulls the reaction to that side. So if I pull something off here, it drives the reaction to the right. Changes in pressure only affect reactions with gases in them. If you increase the pressure, it causes the reaction to shift to the side of the reaction with less moles of gas, or fewer moles. Decreasing the pressure gives you more space so you can accommodate more moles of gas. Gas takes up space. If you decrease the pressure, there's more space. It'll favor the side with more moles of gas. So here we have 1 mole of N2O and 2 moles of NO2. If you increase pressure on this system, these 2 moles are going to get forced together and squished, and they're going to try to take up the space of 1 mole over here, and that'll drive the reaction to the left. If you decrease the pressure, these 2 moles can expand to fill their container, and it drives the reaction to the right. Changing temperature is a little bit more complex because we have to think about several things. If you decrease the temperature and it's endothermic, you're decreasing a reactant, so the shift goes to the left, to the reactant side. If you decrease the temperature and it's exothermic, you're removing heat from the system and you're pulling off product, which forces the reaction to make even more product. If you increase the temperature, it does the opposite. If it's endothermic and it takes in heat, so heat is a reactant, so heat is on this side, and you add more of it, it makes the reaction go forward to the right because it's endothermic. The more heat, the more the reaction can go forward. But if it's exothermic, you want heat on this side for exothermic. Let's do 2 arrows. So if you have heat and you're increasing the heat and it's exothermic, it's trying to give the heat away, and you keep adding more, it forces the reaction backwards. So here's an example. We got the CaCO3 plus heat gives you CaO and CO2 gas. If we add more heat, it's acting like an ingredient and driving the reaction forward. If we remove heat, we drive the reaction the opposite direction. Adding a catalyst basically does nothing, because for an equilibrium to be disturbed, you have to be at equilibrium. The catalyst gets you to equilibrium and it gets you there faster, but once you're at the established equilibrium, according to LeChatlier's principle, adding a catalyst doesn't change the reactants and product ratio. So catalysts basically do nothing in terms of LeChatlier. Now, KEQ, the equilibrium constant, is a constant at a given temperature. Remember when we talked about the equilibrium constant for water, Kw, equals 1 times 10 to the minus 14, and that changes with temperature, and we proved that in a homework problem? So we know equilibrium constants change with temperature. So KEQ is changed by temperature only. So if the temperature changes and the equilibrium shifts to the right in favoring the products, your ratio of products over reactants gets to be a bigger number and KEQ increases. If the temperature changes and the equilibrium shifts to the left, means you have less product, more reactant, your products over reactants is a smaller value and your equilibrium constant decreases. So let's try a couple problems. What effect do each of the following changes have on this equilibrium position, as in side, left or right, for the reversible reaction? So 1 mole of gas, 2 moles of gas. Endothermic, heat's a reactant. So if we add Cl2, we're adding Cl2, it's going to push the reaction to the right, or to the left, to the product side. So remember, adding things acts as a push, decreasing things acts as a pull. We're going to increase the pressure on the system. 2 moles on the product side, 1 mole on the reactant side. If you increase the pressure, it's going to squish the molecules together. It's going to favor 1 mole of gas instead of 2 moles of gas. So it's going to shift to the left. If you remove heat, and heat is a reactant, and that's basically like removing a reactant, removing things acts as a pull. Removing the heat will reverse the reaction, favoring the reverse reaction, making PCl3 and Cl2 recombine to form PCl5. If you remove the PCl3 as it's formed, remember removing things acts like a pull. You're removing this, you're pulling the reaction to the right. So we're going to talk about the Haber process. This is the reaction that was on the first slide. Before we do that, I would like to draw your attention to the fact that this slide shows a chemical factory to make ammonia. And there's a lot of things that have to happen to make ammonia and make it safe. Ammonia is used in fertilizer, and you've heard of fertilizer plants blowing up. Let's talk about why. If you have go from 1 and 3, 4 moles of gas over here, and 2 moles of gas over here, and notice that it's exothermic, let's look what happens when we do some things to this reaction. If we increase the N2, we put pressure on the system, equilibrium will shift to the right. When we shift the equilibrium to the right, the NH3 increases. Equilibrium constant, no change. As a matter of fact, no C. Nothing changes the equilibrium constant except changing the temperature. All right, let's look at removing H2. If we remove H2, removing things acts like a pull and it pulls it to the left. The N2 concentration actually increases. When you pull the reaction to the left, the NH3 is decomposing and making more N2. So then the NH3 is decreasing. Adding NH3 acts like a push and pushes the reaction to the reverse, so the equilibrium shifts to the left. The N2 will increase as the NH3 decomposes. If we increase the temperature, we increase the heat, we're increasing a product, so we're driving the reaction backwards. So increasing, we're going to shift to the left. The N2 is going to increase as more NH3 decomposes into N2, so the NH3 will decrease. Please notice that when the N2 increases, the NH3 decreases, because that's what equilibrium means. If we increase the volume, that's a decrease of the pressure. It means we have room for more moles. That favors this side with 4 moles. So the equilibrium is going to go to the left if we increase the volume. And the N2 will increase as more of that NH3 decomposes and the NH3 is decreasing. If you add a catalyst, it makes no change in the equilibrium position. It just gets you to equilibrium faster. Once you've established the equilibrium, then you can perturb it using LeChatlier's principles. So here is a chemical plant that makes NH3. Let's talk about the design. It has to remove heat at a high enough rate to keep it cooled so there's no explosions. It has to be under pressure, so these 4 moles of gas are getting pressed upon so the reaction goes forward. You don't want the reaction to go backwards and cause any pressure problems on the left side because that could cause explosions. H2 hydrogen gas is extremely flammable and dangerous and explosive. So when you make your chemical power plant and design it, you have to remove heat and keep it under pressure at all times. So that's how that goes. The homework that goes along with this is actually called Worksheet 17.3, LeChatlier's principle, in the homework packet. And see me if you have questions.